In this video, I give one definition. Definition is equivalent sets, and one theorem on this. Theorem on equivalent sets. Then, if time permits, I start this countability of sets. Now, equivalent sets in elementary treatise on set theory. How to define two sets are equal? A is equal to B means we say that two sets are equal. We write like this: if A is exactly equal to B, or A is the duplicate of B. But now this definition is now generalized. We define two sets are equivalent sets, and we denote this notation: A is equivalent to B. Or we say that A and B are cardinally equal. A is cardinally equivalent to B. See, the definition is like this. Suppose A and B are any two non-empty sets. Then we say that A is equivalent to B. See the notation. If there exists a mapping, or function, f from A to B, which is bijection, that means A is cardinally equivalent to B, or A is equivalent to B if there exists a function or mapping f from A to B which is bijection. What do you mean by bijection? Bijection means one to one, as well as onto. F is 1 as well as onto. Again, in set theory, in this semester, you have not studied functions. In your syllabus, it is not there. That is why I have not explained also functions. But in POC classes, you have studied about functions. When do you say that function is 1? A function f from A to B is said to be 1, or it is called injection. It is called injection 1, if f of x1 is equal to f of x2 implies x1 is equal to x2. Suppose x1, x2 belongs to A. If f of x1 is equal to f of x2 implies x1 is equal to x2, then function is said to be 1. What does this imply? This gives different elements have different images. You know what is a function? Function means suppose A and B are any two non-empty sets. I take for definiteness. Suppose it consists of 1, 2, 3, and it consists of A, B, C, D, E, F. Then suppose F is defined like this: 1 is related with A, 2 with B, 3 with C, 4 with F. Then this is 1. This condition implies different elements have different images. Therefore, it is 1. See, onto means a function f is said to be onto, or it is called surjection. Onto, if for every y belongs to B is called codomain, there exists x belongs to A, such that f of x is equal to y. So I explain what is the meaning of this. See, 1 means, what do you mean by 1? Definition means you have to define like this. A function f from A to B is said to be 1 or injection if f of x1 is equal to f of x2 implies x1 is equal to x2. What does this imply? This implies if the function is 1, different elements have different images. This is 1 function. because different elements 1, 2, 3, 4 have different elements, different images. No two elements are related with same element of this B. Therefore, it is 1, 1. What do you mean by onto? Onto means for every y belongs to B, there exists, for all y belongs to B, there exists x belongs to A such that fx is equal to y. This implies every element of the codomain. So I take B, this as A consists of 1, 2, 3, 4. This consists of A, B, C. I take A, B, C. Then 1 is related with A, suppose 2 with B, 3 with C, 3 with B, 4 is also with C. This is a function. 2, 3 may be related with same element. But 2 should not be related with two elements. 2 should not be related with B and C also. 2, 3 may be related with B. It is a function. Now you can see the difference here. In this second case, I take this as G. In this second case, this all the elements of B is called codomain, are the images. But here D and D are not the images. This is strictly 1, 1. This is strictly onto. It is not 1, 1. It is only onto. This is only 1, 1. That is the definition of 1, 1 and onto functions. Now, since we have used here the definition equivalent sets, A and B are said to be equivalent. Equivalent is different, equal sets are different. Equivalent sets, if there exists a mapping from F from A to B, which is a bijection, means 1, 1 as well as onto, there should exist 1 to 1 function. When you say that function is both 1, 1 and onto, say both 1, 1 and onto means, say I take this diagrammatic representation of the function A. Suppose this is B, I take finite elements here 1, 2, 3. Here I take A, B, C. Suppose 1 is related with A, 2 with B, 3 with C. Now what happens? It is 1, 1. Why it is 1, 1? Different elements of this domain have different images. A, B, C are called images. A is image of 1, B is image of 2, and so on. Now, this is onto also. Why it is onto? It is onto because all the elements of the codomain are images of some elements. Therefore, it is onto. Hence, it is 1, 1 as well as onto. Now, this is called 1 to 1 function. 1, 1 as well as onto, or it is called bijection. Now go to this definition. When you say that two sets are equal or equivalent, two sets are equivalent if there exists a function from A to B which is 1, 1 as well as onto, or they are same cardinality. We say that two sets have same cardinality. In our further study of countability, we use this definition of functions 1, 1 as well as onto functions. Now, I state and prove one theorem here. Theorem is like this. I hope definition is clear. All of you have followed the definition. Now, theorem is like this. Statement is like this. Let S be a collection of sets. The relation in S defined by A is equivalent to B. Is an equivalence relation. What is the relation defined here? S is the non-empty sets, collection of non-empty sets, and the relation is defined by A is equivalent to B. This is the relation. Then this relation is prove that it is equivalence relation. You have studied relations. Also, what is equivalence relation? When we say that relation is equivalence, a relation R is said to be equivalence if it is, first is it should be reflexive, symmetric and transitive. Relation is said to be equivalence if it is reflexive, symmetric and transitive. What is the relation here? Relation is equivalent to, A is equivalent to B. Prove that this relation is equivalence. What you have to prove now? It is reflexive, symmetric, transitive. Now, when you say that the two sets are equivalent means we say that A is equivalent to B if there exists a function f from A to B which is a bijection. Now what is the relation here? A is equivalent to B. When you say that A is equivalent to B, if there exists a function f from A to B which is a bijection. Now the proof is like this. First I prove that the relation is reflexive. This relation is equivalent. This is reflexive. For that, consider an identity mapping I from A to A. How it is defined? I from A to A is defined. I from A to A, it is defined like this. How to define? I of A is equal to A. This is called identity function. That means identity function means A is related with A, B is related with B, C is related with C, and so on. That is called identity function. And this identity function is always a bijection, one-to-one function. See, the interesting thing is we do not prove that identity function is one-to-one. We know that I give the statement here. We know that identity function is one-to-one bijection. Therefore, what happens? There exists a bijection from A to A. Therefore, A is equivalent to A. First thing, therefore it is reflexive. Second thing is symmetric. Symmetric means, what do you do? Relation is symmetric means if A is equivalent to B, prove that B is equivalent to A. Let A is equivalent to B. SC non-empty set here. It consists of collection of sets here, and suppose A is equivalent to B. This implies there exists a function f from A to B, which is a bijection. What do you mean by bijection? 1, as well as 1, 2. Again here, if f from A to B is a bijection 1 to 1, then only f inverse exists, and f inverse is function from B to A. If f from A to B is 1 to 1, f inverse from B to A is also a bijection. So what happens? F inverse from B to A is bijection means B is equivalent to A. Therefore, if A is equivalent to B, B is equivalent to A. So the relation is symmetric. What is the relation? Equivalent to is symmetric. So in this case also we have not proved f from A to B is bijection, then f inverse from B to A is also bijection. That is a different topic. It is a different topic. And now in first year semester B.Sc 1 in new syllabus it is added. That is functions is added, and we prove that if f from A to B is a bijection, then only f inverse exists, and f inverse is also bijection. But in this theorem, important thing is if you write like this, it is sufficient. What is that? A is equivalent to B. Suppose A is equivalent to B. There exists a function f from A to B which is a bijection. If f from A to B is bijection, then f inverse exists. What is the function f inverse? It is function from B to A. It is also a bijection. Therefore, B is equivalent to A. Hence, relation is symmetric. Now, it remains to prove that this relation is equivalent to is transitive. For that, let f from A to B, or I take A is equivalent to B. Let A is equivalent to B. Then there exists f from A to B which is a bijection. And let B is equivalent to C. What does this imply? There exists function g from B to C which is bijection. Now two functions are there. F is a function from A to B and g is a function from B to C. Suppose there are two functions. See, the important thing is the codomain of f is domain of g. Two functions are like this. Codomain of f is domain of B. And one more thing is both are f and g are one-to-one functions. Now, by property of functions, there exists a composite function. We write g composition f or simply gf. There exists a function g composition f from A to C, and this function is again a bijection. I explain once again. Suppose A is equivalent to B, then f from A to B is bijection. Also B is equivalent to C, then there exists a function g from B to C which is bijection. Now, if two functions are like this, f and g, like this, then g composition f is a function which is defined from A to C. And the important thing is it is also a bijection. Now, what does this imply? There is a bijection from A to C means A is equivalent to C. Therefore, A is equivalent to B, B is equivalent to C, implies A is equivalent to C. Hence, this relation is transitive. Therefore, the relation equivalent to on collection of sets is an equivalence relation. From examination point of view, the previous theorem is very important. It is asked in the KUD examinations. Now, next concept is finite and infinite sets. Again, in elementary treatise on set theory, we have defined finite set means a set containing of finite elements. Infinite means it contains infinite elements. Now, we define infinite set like this. See the definition of infinite set. A set is said to be infinite if it is equivalent to its proper subset. A set capital A is said to be infinite if it is equivalent to a proper subset of A. What do you mean by proper subset of A? If B is contained in A and A contains at least one element which is not in B, then you see that B is proper subset of A. Now, A is infinite means A is equivalent to a proper subset of B. When you say that A is equivalent to B, B must be subset of A, proper subset. A is equivalent to B means there should exist a bijection from A to B. B is a proper subset of A. There should exist a bijection from A to B. Then A is said to be infinite. Then what is the example for infinite set? I say n is infinite. What is n? Set of natural numbers. It is infinite because take set of all even integers. What are even integers? N means natural numbers. You know this is a set 1, 2, 3 like this. And E. What is E? E is even integers. It consists of 2, 4, 6 and so on. Now E is contained in A and there exists a function f from n to a. I define this as f of n is equal to 2n, where n belongs to n. Then I define a function f from n to e by f of n is equal to 2n. Now how this function is defined? Set of natural numbers are like this: 1, 2, 3, 4, etc. 1, 2, 3, 4, 5, etc. Now this E consists of 2, 4, 6, 8, etc. Now 1 is related with 2, 2 with 4, 3 with 6, 4 with 8, etc. Under this function, you follow this one. F from n to e is defined by f of n is 2n, and under this mapping, how the elements are related? 1 is related with 2, 2 with 4. This is e, this is n. 3 with 6, 4 with 8, etc. Now what happens? This function is f is 1 to 1, 1 1 as well as on 2. Therefore, it is a bijection. Bijection means n is equivalent to e. N is equal to proper subset of itself. Therefore, n is infinite. So how to define infinite set? Infinite means if a set is equivalent to its proper subset, then it is said to be infinite. Now, further, finite, infinite is over. Next is countable, uncountable set. Very important concept, interesting concept. Countable, uncountable set. What do you mean by countable set? Countable means I write 1, 2, 3, 4. It is countable. I say that it is countably finite. Uncountable means 1, 2, 3, 4, etc. What is this? It is, I say it is also countable, because 1, 2, 3, 4 means next we can guess what is the element, next element. What is the next element? 5, next 6 and so on. Even though it is infinite, we say that it is countable. It is countably finite, it is countable, countably infinite it is. This is next concept, and the heading is countability of sets. Countability of sets. This is the next topic, countability.